Hello there, Mr. Sutton here with this lesson on polar functions, slope and basic area. In this one, we are going to be finding slopes of polar functions, whatever those are. We'll talk about that in a minute. And also figuring out area between curves of polar functions. Let's talk a little bit more about polar functions now. A polar function, something of the form r equals some function of theta, takes an angle as the input and gives you the distance from the origin, which we call r. And by the way, the origin is now called the pole. That's why it's called polar functions. This distance from the origin is now going to be your output. And since we can now get negative r values, if you ever get a negative r value, that just means we're going backwards in a certain direction. So if you had a negative r in the 180 direction, that means you'd be going to the right rather than the left a certain amount. Anyway, the way we connect these polar points is we're going to be going from smaller to larger angles rather than left to right. So just to get a sense of how these things are graphed, because I think that helps, change your calculator to polar graphing mode, which I'll show you how to do in a sec, and then set up your window to be from 0 to 2 pi and sketch each of these using zoom 0. And feel free to follow along on this first one. So to get to polar mode, we just go to mode, and down here where it says func, we arrow down there and arrow over to pole, press enter. Now we're in polar mode. If you go to y equals, you'll notice that we now have r's instead of y equals. We'll just graph r equals 2 for this first one. And in window, we now have a theta min and a theta max, which I'm going to set up to be between 0 and 2 pi. If we do zoom 0 now, it'll use those angles to graph things. And we get a circle out of that first one. Now something cool you can do in y equals, if you arrow over to this little dash here and press enter a couple times, you get this little dash with a circle. Now if we graph this, it graphs it more slowly, and this little ball is telling us exactly where our little particle is. Alright, so we get a circle out of that first one. Now you can see the order we graphed things in. We started with the angle of 0, and that gave us a radius of 2. And as we increased our angle, we were still the same distance from the center. That's why we're getting this circle. If you go ahead and graph the next one, it's kind of interesting. So graphing out 2 sine of theta, I'll just add a 2 sine of theta here. And if you're wondering where the theta button is, it's just the X button now. If we graph this out, zoom 0, well, now we end up with another circle, but the whole thing is completely above the x-axis, and you'll notice that little ball went around twice. So what's going on here, the first time you go around, you're hitting all the angles between 0 and 180. But now the next time you go around, that's hitting all these angles that are in quadrants 3 and 4. Since those are going to give you negative outputs on the sine function, you're getting negative r values, which means when you're graphing angles here in quadrant 3, your calculator is actually going backwards on those angles and graphing stuff in quadrant 1 again. Kind of crazy. So pause the video and graph the rest of these out. Now this next one gives us just left-right circles. R equals theta gives us this cool shape called the spiral of Archimedes. And this shape down here, this is called a cardioid. This next shape is a special kind of cardioid called a limacon, and we often have to find the area of this little inner loop here. This shape gives us an odd petaled rose, and this other shape gives us an even petaled rose. Now, big difference between these, you may have noticed on this odd one, we actually end up going through all these values twice. So you should not be making any assumptions about what order you're graphing things in or about how many times you're going around. We'll come back to graphing later on, but for now let's do something on the more algebraic calculus end of things. So with this one we have a particle moving along this polar curve. We want to describe its motion at this value here of theta equals pi. Now these types of problems of describe the motion, basic idea here is if you compare the signs of r, which tells you distance from the origin, and dr d theta, how that distance is changing, that just tells you if you're moving toward or away from the origin as you go around in terms of your angles. So pause the video and see what you can conclude based off of this function. All right, so plugging in the theta value for pi for theta, we have 2 minus sine of theta. Sine of theta, or sine of pi, is just going to be 0. So that's going to be 2 minus 0, which is 2. Now, significantly, this is a positive number, so we're going to have to keep that in mind. Now, if we take the derivative of r with respect to theta, so r prime of theta, that's just going to be negative cosine of theta. And if you plug pi into that, negative cosine of pi, well, cosine of pi is already negative, so negative negative 1 gives us positive 1, also a positive number. So if we have a positive r value, and our rate of change is also positive in that r value, that means that we're moving away from the origin. If we have the same sign between r and r theta, we're moving away from the origin. If these signs conflicted with each other, if they were opposites, then we'd be moving toward the origin as the angle increased. For this next problem, we're given the same r and theta as the last example, but now they want the slope of the line tangent to the graph at this point. So if we're thinking tangent lines and slopes, we're thinking derivatives, but we know that if we just take the derivative of this, that doesn't really give us an xy kind of slope, it just gives us how the distance from the origin is changing. So if we want to get slope, we're going to have to express this with an x and a y. We're going to have to express it parametrically. And then we're going to have to use that whole y prime over x prime parametric slope setup to get dy over dx. So we have to start by expressing this with an x and a y. How can we do that? Well, the key is, if we look at a unit circle here, the angle and the radius, we can think of this r as being the distance between the origin and some point on the circle. And then here's your angle. Now, this is an x and a y point right here. So if we drop an altitude and draw a triangle, the base of that triangle is just the x value of that point, and the height of the triangle is just the y value of that point. Now, the reason we drew a triangle is we can use a little SOHCAHTOA magic here. We know that the cosine of theta equals adjacent over hypotenuse, so x over r, which means that if you just want to get the x value from an r and a theta, you can just write that as the radius times the cosine of theta. Now, by the same token, we know that the sine of theta equals opposite over hypotenuse, y over r. So the y value of an angle is just going to be r times the sine of theta. And we've done all this before, but it's been a while, so now it's actually going to be very helpful to remember this relationship. So going back here, let's get our x function first, our x parametric first. So that's going to be the radius, which is 2 minus sine of theta, times cosine of theta, like so. And it's going to be helpful. We're going to have to get x prime out of this eventually. So before I do that, let me just distribute this because I don't really feel like dealing with a product rule. So we've got 2 cosine of theta minus sine theta cosine of theta. Now, at this point, if you're taking the derivative, you've got another product rule with this sine cosine. So one little trick you should use as you go along with these is you can often simplify using the identity 2 sine of theta cosine theta equals sine of 2 theta. That's one of our double angle identities. And another one that's pretty closely related, if you see just sine of theta cosine of theta without the 2 out in front, well, if you divide this whole equation by 2, that would be equivalent, sine theta cosine theta, that would be equivalent to half sine of 2 theta. So if you make these two conversions, you can often avoid using the product rule. Here, for example, instead of writing sine of theta cosine of theta, I can write here minus 1/2 sine of 2 theta. And now instead of a gnarly product rule, I just have a small chain rule. So taking this derivative, this is x prime of theta now, we've got negative 2 sine of theta. And then over here, we're going to have minus, let's see, this would be 1/2 cosine of 2 theta times a tail of 2, which would cancel out that 1/2. So just minus cosine of 2 theta. All right, pause the video and see if you can figure out y and y prime based off of what we just said here. So now the y function, that's going to be r sine of theta. So that's the radius here, 2 minus sine of theta times the sine of theta. And multiplying that out, I've got 2 sine of theta minus 2 sine squared of theta. Now, I don't have to really worry about any product rules here. I can just take the derivative. So this is going to be 2 cosine of theta, and this is going to require a chain rule. So we're going to have minus 2 sine of theta times the derivative of sine, which is cosine of theta, But at this point, it might make sense to simplify this 2 sine cosine as sine of 2 theta. Just make it easier to plug things in. Speaking of plugging things in, again, we know that dy over dx parametrically is y prime over x prime, so let's go ahead and do that. So if we're evaluating at theta equals pi, that means we're doing y prime of pi over x prime of pi. So y prime of pi, that's all this stuff right here with pi plugged in. X prime of pi was this stuff here with pi plugged in. Simplifying that a little bit, and you would be expected to do this without a calculator. Cosine of pi is -1, so this is -2, and sine of pi or even 2 pi is going to be 0. So this is -2 in the numerator. Down here, again, sine of pi is 0, so we don't worry about that. Cosine of 2 pi, that's 1, so this is just -1 down here, which gives us 2 for the slope of this thing at pi. At this point, we're going to start talking about polar area. Now, when you were finding area under rectangular curves, things in y equals x form, you were adding up the area of a bunch of skinny rectangles. Well, now with polar curves, we're going to add up the infinite number of skinny sectors that we can chop one of these polar curves into. And you can think of these as like little mini pizza slices or even just radius strips. So the area of one of these sectors, which is going to be important, we need the r and the theta in order to find this sector area. And we can express this area, if you've never seen this formula before, as the area of a whole circle, pi r squared, times the proportion, the piece of it that we actually want. So that would just be your angle divided by the whole 2 pi that you could go to get all the way around the circle. And that simplifies, if you cancel the pi's, to just 1/2 r squared theta. But we want these sector areas to be infinitely small. So to make these really thin, we're going to use d theta instead of theta here. So that's a little small differential in our theta values. So we're basically adding up a whole bunch of 1/2 r squared d thetas. And to add all those together, we need just an integral from a to b, where a and b are both theta values. So this is our polar area formula that we're going to be using over and over again. Now that we've got a formula for polar area, let's take it for a test drive by finding the area inside the cardioid, r equals 2 plus 2 cosine of theta. So before I do anything else on these problems, I like to write that area formula out. So integral from a to b of 1/2 r squared d theta. And that just gives me a roadmap for what I need to find. We actually already have r right here. They always give us that. So we really just need to start by finding these limits of integration. That's really the main mental work on this. So let's figure out our limits of integration for our desired area, which is inside the cardioid. And there's a couple ways you can do this. First off, we can't just assume that we're going from 0 to 2 pi. We often are, but it's not always going to be 0 to 2 pi, because you saw when you graphed out, for example, 2 cosine of theta and 2 sine of theta, we run around the shape twice from 0 to 2 pi. And if you do that with this area formula, you're basically double counting the area. So there's two ways to get your limits. If you have a calculator, you can actually graph it out and use the trace function to see which angles are giving you which parts. So on our calculator, if we go to the y equals in polar mode and actually graph this out here, and then let me just do a zoom 0 on this. Here's the shape that we're using here. So right here. Now what I'm going to do on the calculator, now that I've got this graphed out, is I'm actually going to use this trace function. When you use that, it's going to start you at whatever angle is your starting theta in window. And as you press the right arrow, it's going to take you through the angles, going up by, well, whatever your theta step is in window. It's kind of neat how this works. So as we go through here, we notice that as we get to the theta value of pi, we end up back at the pole here. And as we increase from pi to 2 pi, that takes us the rest of the distance around to where we finally get to 2 pi right here. So we see that by tracing this, we indeed are going from 0 to 2 pi. So this is how you can do it, with a calculator. Now, if you didn't have a calculator, one other way you could do this is plug easy angles into this function just to show you where you were. For example, if you plug in the angle 0, if you do 2 plus 2 cosine of 0, well, cosine of 0 is just 1, so that'd be 2 plus 2, which is 4. This is saying when I'm on the 0 line, I'm going 4 away from the origin, so that would give me this spot right here. Another easy angle would be pi over 2, 90 degrees. You plug that in, 2 plus 2 cosine of 90 would just be 2 plus 0, or 2. That's saying if I go on the 90-degree line, I'm going 2 away from the origin, which would bring me right here. So you could keep plugging in these types of easy angles, and that again would take you all the way around. So once we've done that, we just have to put the 1/2 and the r squared in there, like so. So 1/2 times all that stuff up there squared. Don't forget your d theta. And now this is a calculator problem for this one anyway. So just like before, I'm going to be using Math 9 to get my integral. We're going, in this case, 0 to 2 pi. And in here I've got 1/2. And then one little shortcut you can take here. This is really just r squared. Remember that you actually graphed this thing out. So you can do alpha trace. And if you're still in polar mode, you can pull up your R1 that you put this in. And we're just going to be squaring that. And then go to dx, d theta, press enter, which gives us 18.850 if we round that off. For this last example, they just want us to write an integral expression for the area inside one of the petals on this graph that they gave us. So to do this, a little trick you can use for roses, and by the way, we're still using 1/2 r squared d theta integral. For roses, for petals, you can just solve for where your radius equals 0, because basically you want to figure out, as you go from one pole crossing to the other pole crossing for one of these petals. So we're going to start by doing 2 sine of 4 theta equals 0. Just a little review of solving trig functions. We start by isolating the trig function, so just divide by this 2 here. And now we have to do inverse sine of both sides, or inverse whatever trig function. So we're basically asking, at what angle do I have a y value, because that's what sine is talking about, of 0. That's going to happen at the angles 0, pi, 2 pi, 3 pi, but we only need a few of these. Whatever answers you get, you can divide that by whatever number is next to your theta. So that's going to be theta equaling 0 over 4, which is just 0. Pi over 4 is, well, just pi over 4. And I guess you could keep going. You'd get pi over 2, 3 pi over 4, and so on and so forth. So now this first petal right here, we're starting at 0, and when we get to pi over 4 for the angle, that brings us back for that first petal. And if you weren't really sure that this is the direction you were going, you could always plug in some numbers between 0 and pi over 4, like pi over 6, 30 degrees, and you'd see that, yeah, we do end up in this part right here of this petal. So that means that we're going to be taking an integral from 0 to pi over 4 of, well, we're going to plug this stuff in a minute. But first, a quick little sidebar. Let's say that you had something a little nastier than this to solve, but you were able to use a calculator. Unfortunately, you can't do anything really useful in polar mode other than graph these things. Like, you can't find intersections and pole crossings. But if you want to find zeros and intersections, you can graph this r equals as a y equals in just regular function mode and find the crossings that way. For example, if you went to y equals and graphed this out with x instead of theta, here's what it would look like between 0 and 2 pi. And this is kind of wild, but this is graphing all your r values as y values. So each of these mountains and valleys is actually one of these petals on this graph right here. And this is our first crossing at pi over 4, which is about 0.785 and some change. Anyway, so in here we've got 1/2 r squared d theta. And this is an integral expression, so you're technically done with the problem. But these are often multiple choice problems, and you sometimes have to rewrite your integral without this little 1/2 in here to match it with a multiple choice answer. So to do that, we typically just have to square the stuff and multiply by the 1/2. So we'd have 4 sine squared of 4 theta. 4 times 1/2 would just give us a 2 out here. So we could rewrite this as 2 integral sine squared of 4 theta d theta. This concludes our first look at polar function calculus. Till next time, Mr. Sutton signing off.